Okay, today we're going to start chapter 6, which is going to be all about the normal distribution. So what is a normal distribution? Well, if a random variable has a probability distribution whose graph is continuous, bell-shaped, and symmetric, then it is called a normal distribution. And the graph is itself called a normal distribution curve. Now, let's go over some properties of a normal distribution. So the first one is that a normal distribution curve is bell-shaped. So we've seen that before. In fact, we have like a little example of what that bell-shaped curve looks like off to the side there. And that goes along with number 2 as well. So in a normal distribution, the mean, median, and mode are all equal, and they're located at the center of the distribution. A normal distribution curve is unimodal, which just means that it only has one mode. The curve is symmetric about the mean, which just means that the shape is the same on both sides if you were to put like a vertical line through the center of the curve. The curve is continuous, which means that there's no gaps or holes in it. So you could draw the entire curve without lifting your pencil up off of the paper. The curve never touches the x-axis. So even though it might seem like on the ends here that the curve is getting closer and closer and closer to the x-axis, and it looks like it maybe might cross at some point if you go out far enough, it never actually will. So it just gets increasingly close to it, but it will never actually touch it or cross it. The total area underneath the normal distribution curve is equal to 1, or if you're working with percents, it would be 100%. And number 8 there, the part of, well, number 8 is basically just the empirical rule, which we already learned like back in chapter 1, 2, or 3, one of those, I don't even remember. But the empirical rule was the rule that said that about 68% of the data lies within 1 standard deviation of the mean, about 95 lies within 2 standard deviations, and about 99.7 lies within 3 standard deviations. Okay, now we're going to look at a specific type of distribution first today, and it's called a standard normal distribution. So this is going to be a normal distribution where the mean is equal to 0 and sigma is equal to 1. So whenever the question specifies that it's talking about a standard normal distribution, then you automatically know those 2 facts right there. Now, all normally distributed variables can be transformed into a standard normal variable. And once those x values are transformed, we call them z-scores. Okay, and if you remember back to when we like briefly talked about z-scores, what they tell you is the number of standard deviations that a particular x value is away from the mean. Okay, so once you take your x value and you transform it into a z value or a z-score, that's going to tell you how many standard deviations away from the mean that x value is. Now, what we're going to focus on today first is finding the area underneath the standard normal distribution curve. And to do that, if we were to do it out by hand, what we would have to do is use this formula that I'm going to write up at the top here. So you don't necessarily have to write this down, but I do just want to show you like what is programmed in your calculator, which is how we're going to do those problems. So if you wanted to get the y value on a normal distribution curve, it's this formula right here. So it's e to the negative x minus mu squared divided by 2 sigma squared, that's all in the exponent. Then you divide that by sigma times the square root of 2 pi. So that just simply gives you the y value along the curve. If you actually want to find the area, you would have to take that formula and mix it up with some calculus and actually find like an integral, and that would give you the area. So obviously that's a little bit too advanced for us at this point, so we're just going to rely on the fact that that's programmed into our calculators, and we'll use that. So in your calculator, when you need to find the area underneath a distribution curve, you're going to go to the function normal CDF. Okay, and I'll show you where that is when we do an example. Now, normal CDF is going to require 4 inputs from you. It's going to need to know what the lower bound is, the upper bound, mu, and sigma. Now, the lower bound and upper bound are oftentimes either like positive infinity or negative infinity, and your calculators don't have an infinity button. So the way that we kind of like trick the calculator into doing infinities is this here. So for negative infinity, you're going to type negative E99, and I'll show you how to do that. And then for positive infinity, it's just going to be positive E99. Okay, so that's essentially going to be how we tell the calculator negative infinity and positive infinity. Now, where is that E? So to get the E in your calculator, you're going to hit second comma. And it's a little misleading because it's actually written as like a double E when you look at the calculator button or the front of it. But then it only is going to type one single capital E. So they had to differentiate it somehow because there's also like the alphabetical E on your calculator, so that's already taken up. So the double E that you see on your calculator faceplate is actually the E that we want. So to get that, you just hit second comma. Okay, so let's do an example, and you guys will see how easy this stuff is. So example 1 says to find the area under the standard normal distribution curve to the left of z equals 2.09. So whenever I do these problems, I always like to label what the mean is. That's going to be in the center. So since we're talking about a standard normal curve, I know it's going to be 0. And then my z value is 2.09. So positive 2 is obviously larger than 0. So I know that 2.09 is probably somewhere over there. It's just definitely to the right of 0. And then what we're looking for is the area to the left of that. So I'm going to shade in that area under my curve. And that area is what I'm going to try to find. Okay, so whenever you're finding area under a curve, that's going to be normal CDF. And then we have to now think about what the lower bound and the upper bound on that area is. So the lower bound is, basically like your end point all the way to the left. Well, this curve basically goes on forever to the left. So whenever your lower bound is all the way to the left, that's going to be negative infinity. So we're going to do negative E99 for the lower bound. And then the upper bound is going to be where that shading stops on the right, which is right here at the 2.09. So 2.09 will be your upper bound. And then since it specifically says that it's a standard normal distribution curve, mu is going to be 0 and sigma is going to be 1. Okay, so I'll show you on the 84s how you'll go about typing this in. So normal CDF is found under your distributions. So you're going to hit second bars. So second bars, and then I think it's the second one down. So you want to make sure you're using normal CDF and not PDF. We'll never use PDF. So to type your lower bound, you'll hit the negative and then second comma, and you'll see that it's going to type a capital E there, and then do 99. For your upper bound, you'll just type 2.09. And then mine already had 0 and 1 in there. If yours doesn't, just put those in, and then you'll paste that, and you'll get the answer. Now, if you're working with an 83, once you go to normal CDF, it's gonna like put it up on your front screen, and then you're gonna have to type in those 4 inputs, and you have to make sure you do them in the correct order. So remember, it always has to go lower bound, upper bound, mu, and sigma. So then you'll actually type negative E99, comma, 2.09, comma, 0, comma, 1, and then do your closing parentheses. And you can see that either way, you get the same answer there. And I do just want to point out, negatives are not the same thing as minus signs in your calculator. So a lot of times students will hit like minus E99, and they'll get an error when they do that. So for negatives, make sure that you're hitting the negative key, which is on the bottom of your calculator there. Okay, so we get approximately 0.9817. And for these, you want to do them to 4 decimal places. So that means that approximately 98.17% of the area is to the left of Z being 2.09. Dr. Insco, do you have any questions on that one?
No, it seems pretty easy.
Okay, do you want to do example 2 and 3?
Sure, so we're going to find the area under the standard normal distribution curve to the right of Z equals negative 1.14. Okay, so that's everything to the right of negative 1.14. But I think you said that the calculator always calculates the area to the left. Is that right?
No, that's going to be when we do our next function.
That's for the inverse normal?
Correct.
Okay, so we're fine here then.
Yep.
Okay, so we're going to calculate everything to the right. Oh, so all you have to do is plug in normal CDF? Is that the command?
Mm-hmm.
And then you want to put the left bound, which we'll put as negative 1.14. And then the right bound, which is E99.
Yep, because it's positive infinity.
Yep. And then the mean is 0. And because this is a standard normal, the standard deviation is 1. And then you hit enter, right?
That's it.
Cool. And so we see that 87.29% of the area is to the right of the z-score negative 1.14. And then example 3, we just, rather than having to put in the E99 or negative E99, we have 2 bounds. So we're going to type in normal CDF of, and we want to put the left bound first. It's normal CDF of negative 1.35, and then comma 1.62, and then 0 and 1, and that will give us the area between those two scores. So it's that area shaded right there to the left. And that's 85 or 85.89% of the area under the bell curve fits between those two bounds, negative 1.35 and positive 1.62. Did I do everything okay?
Yes, I actually have a question. So
Okay.
it said to find the area between 1.62 and negative 1.35. So why couldn't we just put negative 1.62 comma negative 1.35?
You said it had to go lower bound and then upper bound, and so you have to go with the smaller number to the left as the lower bound and then the larger number to the right.
Yep, exactly. So on like 90% of the questions that they'll get on Connect, it'll give them the numbers like from least to greatest, but on some of them, they might switch it up. So you definitely have to pay attention to that. So just make sure that you're always putting the smaller number as your lower bound and the larger number as your upper bound.
Okay,
Because the calculator will still give them the answer. It'll give them a answer. It just won't be correct. So.
Okay, that's good to know.
Yeah. Okay, now a normal distribution curve, it can also be used as a probability distribution curve. So this is actually like a really cool fact that the area under the curve, which is what we've been finding, is the exact same thing as the probability of randomly choosing a certain z value. So by finding the area under the curve, we're also finding the probability that we'll get a z value within that area. So pretty cool fact. And it allows us to now find the probability of z being a certain value. So on example 4, we're now asked to find the probability in part A that our z value is less than 2.09. So essentially, this is the exact same question as example 1 that we already did. So since we're finding the probability that z is less than 2.09, then we're essentially finding the probability that z could be anything from negative infinity up to 2.09. And then the way that you find that probability is to find the area under the curve. So you still do normal CDF and you do everything the exact same way, and your answer is the exact same. So these are basically just like 2 different ways of asking the same thing. So on some questions, you might be asked to find the area under the curve. On other questions, you might be asked to find like the probability that your z value is something. Okay, so the same method to solve them either way. So on part B, it says to find the probability that z is greater than negative 1.14. So the fact that it's greater than means you're finding like from negative 1.14 up to positive infinity, if you think about a number line. So that's the same question as what we already solved in example 2. And I'm sure you see how this is going. So part C, we want to find the probability that z is between negative 1.35 and 1.62. So if you got a question like that, you would solve it the exact same way as what we did in example 3.
Okay. So these are like, these probabilities, this is like, if you were to get a score, let's say on like a health test or something, and this is calculating the probability that your score would fall between negative 1.35 standard deviations from the mean and up to 1.62 standard deviations from the mean, right? So this is like,
Yep.
what's that probability if it was just left up to chance or something?
Mm-hmm.
Okay.
Yep, as long as your data is normally distributed, then yep.
Cool.
Okay, so now we're going to kind of go the other way with it. So now we're going to be looking for those specific z values. And the way that we do that is we have to know the area to the left of that specific z-score. Now, why is it the area to the left? Well, that's just like the standard way it's kind of always been done. So it's what, it's how your calculator is programmed. And it's how most tables work. If you maybe did stats in high school and you kind of saw some normal distribution tables when you took that class, they all work by telling or figuring out what the area to the left of that z-score is. Okay, so you want to make sure you remember that. Now the function that you're actually going to go to in your calculator, it's called inverse norm. So it stands for inverse normal. And then it needs 3 inputs. So it needs the area to the left of that z-score that you're looking for, or that z value, and then mu and sigma. So 3 inputs for that one. Okay, so let's do a couple examples here. So the first one on part A, we can see that we're looking for this z value here. So we're looking for the value on that horizontal number line. And we have this area here, the 0.0239. So Dr. Insco, is this area right here, the 0.0239, is that the area to the left of that z value?
No, it's the area to the right.
Yeah, good. So they gave us the area to the right, but we need the area to the left if we're going to go ahead and put this into our calculator. So we can figure this out. This is not too bad. So let's see, if you were paying attention when I was reading those properties at the beginning, what did we say that the total area under the curve is equal to?
The total area under the curve should be 1, right?
Yeah, good. So we want that area to the left. So we can use the fact that the total area underneath the entire curve is equal to 1. Okay, so if we just want the area to the left and we know the area to the right, then all you have to do is 1 minus the area to the right. So 1 minus 0.0239, that comes out to be 0.9761. And that's going to be the area to the left. So that's going to be the number that we're going to put into our calculator when we go to inverse norm. So inverse norm is found in the same place that we did normal CDF. So you'll do second bars, and then it's the third one down. It's inverse norm. And I think I'll actually show you on the calculator. Yeah, I do. So second bars, third one down is inverse norm. And then it's just going to ask you the area. So you'll put 0.9761. And then mu and sigma are 0. So you get about 1.98. Z values, you always round to 2 decimal places. And then for the 83s, I don't have a picture here, but you do it the same way. So you go to inverse norm, it'll pop it up on your screen, and you're going to type in then 0.9761, comma 0, comma 1, close your parentheses, and you'll get the same answer. So we get a Z value of approximately 1.98. Okay, do you want to explain part B?
I'll give it my best shot.
All right.
Okay, so this looks like maybe we have to do a compound sort of thing where we know that we want to calculate the area of that shaded region. And so first what we're going to do is we're going to calculate the area from that z-score to the left. And then we use the fact that the bell curve is symmetric. And so like half of the area is to the left of 0 there. So I think we're just going to calculate the area to the left of that, we're going to calculate the z-score to the left of that and then add that up, right? So we're going to add 1/2 to the 0.4066, and that'll give us 0.9066 for that pink shaded area. That's what I wanted to say. And then we can plug it into the calculator. So it's that easy once we do that quick addition. So we want inverse norm of 0.9066, and then again 0 and 1 because this is a standard normal distribution. And we calculate a z-score of 1.32. Okay.
Perfect. Yeah, so you know, you're not going to be able to approach these always in the exact same way. You know, if you're given the area to the right, then you'll do like 1 minus the area to the right to get to the area to the left. Here, you know, you're given just a piece of it to the right. So now you can use the fact that like the area the area on each side is equal to 1/2 because like you said, it's symmetric. So you would add 0.5 with that area, and that way you're getting the entire area to the left.
Well, this is just like a question that the book put together to just test to see if people were paying attention.
Yeah. Yeah, and let's actually, that's the end of the section, but let's do just a couple of practice problems here. I think we'll see like a couple other situations that could happen.
All right, great.
Okay, so let's just kind of review what we learned today as far as like the calculator function. So if you want to find the area under the curve, or if you want to find a probability, what function is that in your calculator?
Normal CDF.
Good. So normal CDF, and that has the 4 inputs, lower bound, upper bound, mu, and sigma.
Yeah.
And then if you're trying to find a specific z value or an x value, what function is that?
Inverse norm.
Inverse
Or
norm.
norm. Yeah.
Yep, and you need to tell the calculator the area to the?
To the left.
To the left, yep, and then mu and sigma.
Are you going to mention Beyonce in this or no?
No, I wasn't going to.
Okay.
Do you want to mention it? I giggle every time I think about it.
So before we were filming this, Karen says that to help students remember that you always need to put in the thing to the left. She sings Beyonce's to the left, everything in a box to the left. Is that what the lyric is? Everything you own in the box to the left? Yeah.
Yes. I'm sure they know what song that is.
Yeah, exactly. That's a total earworm, so I'm sure they know what we're talking about here.
Yeah, so every time I say the phrase to the left, I always hear that song in my head. It usually makes me laugh.
So hopefully people will remember that at our expense.
Yeah. Okay, so just a couple practice ones. So find the area under the standard normal curve between -1.46 and -1.98. So
that one's going to have a -1.98. It's got to be the lower bound, right? Because that's more negative.
More negative, yep. So it's smaller.
So I guess that's the only hard part, right? And then once you know that, you plug those numbers in and hit enter.
Yeah, that is the only hard part. In fact, on like the test, I normally put that exact question on there, and still so many students get it wrong because they just put the numbers in order that they see them and don't actually put them in order from least to greatest. So yep, so that's all you have to do there. So normal CDF gets you the area under the curve. And then number 2, we want to find the probability that z is greater than 2.51. So for greater than 2.51, you know, you could draw it out. You could certainly draw like a curve, put 2.51 on it. And then for greater than, that means you would want to shade to the right. So you would start at 2.51 and then you would shade up to positive infinity. So if it helps you to draw it out, go for it. If not, you might be able to just like reason out that a greater than sign means you're going towards positive infinity. So we're still going to do normal CDF here. 2.51 will be the lower bound, E99 will be the upper bound, and then 0 and 1. And we end up with 0.0060. Do you want to take B?
Yeah, so for B, we're going to the left of negative 1.77. So again, you just want to go from negative infinity to negative 1.77, which means you want to use the negative E99 key in your calculator as the left bound, and the negative 1.77 as the right bound, and again, 0 and 1. And we'll calculate a probability of about, well, 0.0384, so that's 3.84%. Is that right? Okay.
Yep. I didn't put the percents on there, but if you want to, you can. Okay, and then these are the ones that are a little bit more fun, I think. So now we're finding the Z value. Okay, so whenever you're finding the actual value on your horizontal number line, that's going to be inverse norm. And we just need to figure out the area to the left of that Z value so we can tell it to the calculator. So on part A, they did not give us the area to the left. So the area to the left is this kind of white area over here. So that's what we have to figure out. So can you think of a way that we could get what that area is?
Yeah, everything to the left of 0 is a half. So you take a half minus that 0.4175.
Yep.
And that's going to be, not quite sure, like
I'll help you out with
0.08.
that.
Okay, 0.0825. I should be able to do that in my head, but.
Yep, so then you'll do inverse norm with 0.0825, 0, 1, and that'll come out to be about negative 1.39. Okay, and then how about part B?
Part B looks easy to me. Am I missing something? Don't
No,
just do inf norm of 0.9671, 0, 1.
Well, why do we just get to jump to inverse norm? Why don't we have to do like something with a 1 or something with a 0.5?
Because that's the area to the left of that one value, I guess.
Yeah, so the value we're trying to find, the Z value, we want the entire area to the left, and that's what they gave us. So sometimes on questions, they'll just straight up give you the entire area to the left. So you can just use that, do inverse norm, and that'll get you your Z value.
All right.
And that's it. That's the end of section 6.1.
Cool. Thanks, Karen.